Hello again. Let's talk about ranking algorithms now. All right, so uh, the main ones we're going to talk about in this course, we're going to look at the vector space model, and in particular, cosine similarity. And this model, it's still applicable in certain domains and at certain times. But I would say that it lived, primarily from the 60s through 1980s. Okay. And in fact, maybe the 60s is even too early. I should really actually check when was the vector space invented, but it should be in the 60s because I have a book from Gerard Salton uh, going over all of the huge amount of research that he has, and it came out in 1971, I believe. So yeah, he had to have been doing that work in the 60s. Now it continued on through the 80s, and this was a very dominant retrieval method, and all sorts of things were done to try to figure out how to improve retrieval quality. Then in the basically in the 90s, Trek came to be, and we started to have these evaluations and everyone working together. Not me, I was still a student in the 1990s, all right? Not that old. But they, as part of that, one of the big things that came out of the work done during that time period was BM25. Which is best match, and 25, maybe the 25th one they tried. I forget the exact details, or it's some combination of letting us know something about the formulation of the best match algorithm that they had. And I would say that this algorithm has been living quite strongly from the 1990s to today. My understanding is that, if you use the open source Lucene retrieval engine, now finally they've gone and gotten BM25 in there. My understanding is that certainly a lot of the key ideas about how to weight terms and do a high quality retrieval have been part of major search engines. And so this is a very important ranking algorithm. It works really well. A lot led up to it, and a lot went into it as well to figure it out. And so we're going to learn that, and that's what you'll implement for homework 4. And then language modeling came on the scenes. This language modeling approach to information retrieval, and this is basically post 2000 to today. So there's still research on language modeling, in particular the notion where language modeling has gone. So language modeling, I'll just say, it came out of a lot of study, in particular dealing with speech and other aspects of solving problems with language. And so then those sorts of models influenced and were people learned and adopted and applied them to information retrieval, and they were quite successful. One of the big hopes was that the theory here would allow greater gains in performance. I think what's really ended up happening was, it's unclear whether or not we truly were able to surpass anything in language modeling with what happened with BM25. But notions and ideas of language modeling are present in the deep learning approaches that are now sweeping a lot of the recent research. And so there's language modeling. They're building these deep these language models. They train and they learn, and they feed them huge amounts. They basically feed them the web, and they learn language from all of that. And then they're able to use these for all sorts of other techniques and improving ranking performance. So that is this progression. These are, this is the last couple of years. Really, to see this sort of stuff take off. We've seen the video, or perhaps you haven't, but the video I recommended from Google. I mean, they're actively using these techniques today, so they've been deployed at an industrial level as well. We will not have a chance to talk about deep learning in this course. Again, MSCI 641, the text analytics course, gets into a lot of the neural net and other aspects, and that would be a course where you could learn some of those techniques. All right, so that's sort of the scope, and you can see this pattern in time. But of course, there's been other things, and you could say, competing during these times, the early years were Boolean retrieval algorithms, but all of this history is, we're going to be using statistics and counting and coming up with a method to rank documents, not just to get a set of documents retrieved for us as is done in Boolean retrieval. I mean, all of the quality and performance that you have been experienced your whole life on web search engines is a direct result of that research. It's not Boolean retrieval, which, sure, we learned that doesn't work well on its own. So let's start talking about our first major area then, vector space. All right. It seems like I'm about to due for a new pen. All right. Let me see if I can grab one that works better. We'll try these out. All right. I'm going to start off by drawing a very big matrix here. I guess it's not big, but I know that in reality it really is. If we were to make this in the computer, it would be gigantic, and we will never make this matrix in the computer. Not in a full form. We effectively make it in a sparse form. All right, so this matrix, we have documents. So each row represents a document in our collection, and each column represents a word. All right, where we'll use T for term, sub K. All right, D sub I for the document I. So we have documents by words, and what we will store then in a cell of this matrix is a weight, Wi sub K, and this weight will be greater than or equal to 0. All right, so what are these weights? 0 means the word is not present in the document. So if we don't see this word, these words are the tokens that we get from doing our lexical processing. After our stemming, it's the final set of words. 0 means it's not present, whereas values which are greater than 0 indicate the degree of importance that we place on this word for this document. All right. So let's take a look at this here. A document is a n-dimensional vector. Vector of word weights. All right, so each row, in the matrix, we can say, oh, we have this document, and here's its vector. All right. By the way, of course, as well, we could say here's a word, and here's its vector. it's kind of a nice symmetry to this way of thinking. When we have a vector representing the document, again, it's going to tell us basically which words are in the document and how much importance do we place on it. N-dimensional, well, how many words do we have in our vocabulary? That's the N. All right. Now, in this vector space, just to note that here, words are our features that we were talking about for the general nature of ranking algorithms. And yeah, we don't store this matrix. This is an abstraction for us to think about vector space and to talk about it. We don't store this directly and go, all right, let's look at our two-dimensional matrix and use it in our computations. Why? Well, just think about, even for the data collection you have, so let's say this is on the order of 100,000 documents and words. Oh, even if it was 100,000, only 100,000 words, I'm sure there's more than 100,000 words, so if you've got 100,000 words and you multiply it by 100,000, that's another 5 zeros, 1, 2, 3, 4, 5. So we would have in this, we would have a cool billion cells in this matrix. Oh, I actually did that wrong. Sorry, I'm not. Never try to do things on the fly. Always be really careful. I'm sorry. So there we go. So those are the millions. Yeah, 10 billion. So 10 billion cells. All right. Anyways, 10 billion cells. Oh, what's 10 billion cells? Well, let's just say you want it to store, it's a weight. So you're going to store a floating point value. Let's say it's only 32 bits. So or 4 bytes. All right. So 4 bytes times 10 billion mega giga. So that's just for your small collection, that'd be 40 gigabytes that you would need to store in memory, because you wouldn't be accessing a matrix like this on disk. You'd be storing it in some, so sure, maybe you've got 40 gigabytes of RAM and maybe you got a big server, but you can see I already actually probably underestimated the vocabulary size, and this number of documents is really small. It's easy to be doing, again, the web, we'd be talking about on the order of, if we were just doing English, about 1 billion documents alone. And then we would have in excess of a gigantic, we just don't store these in memory. Certainly your laptops, most of you don't have the memory for this, even at the small scale. So no, just want to make that clear, because some people think, oh yeah, I'll just go and make a nice big matrix and use, MATLAB and things like that. No, not going to happen. Well, it could, but not very feasible. All right, so let's look at cosine similarity in the vector space. This is how we're going to compute our scores for our documents. All right. The first thing that we want to do is to note that, again, just remember that we're going to treat the query as a document, then do matching between the query and the documents. So this is really sort of a big idea to keep in mind, that the user types in this query, and we're just going to simply treat it as a small little document. And so you're going to be sure that when they type in the query, like you did when you did the Boolean retrieval, that you turn it into tokens exactly the same way that you did the document. Otherwise, you're not going to have matches. You're going to have problems. All right, so we'll try another pen. Soon I'll have to grab a brand new pen. All right. Now, before we get into this, I want you to recall the following from your math courses. That if we have two vectors, let's say we have x and we have y, and we have some angle theta between x and y. If we take the dot product of x and y, this is equal to the magnitudes of x times y times by the cosine of theta, which we could rewrite then to say that the cosine of theta is x dot y all over the length of x and the length of y. All right. So you're like, I don't remember that. Or maybe you're like, of course I remember it. Either way, it's important to know this. So we can obtain the cosine of this angle by doing this calculation. We take the dot product of x and y and we divide it by the product of their lengths. And I just drew this in 2 dimensions. And you're really used to remembering, oh yeah, x is a point, 2-dimensional space, and y is a 2-dimensional space. And oh, I remember doing that formula. It's totally okay for this to be n-dimensional. Everything the math is all exactly the same. And you're like, what is an angle in n-dimensional space? And how am I supposed to think about n-dimensional space for words? And I have to tell you, I don't know. There's no way. Like, I can't visualize, 100,000 dimensions. And what does a vector look in a 100-dimensional space? And what does it mean to have an angle between them? Well, it is what it is, all right? I think we should note and remember, though, as part of our recollection, is that when x is orthogonal to y, the cosine of theta is equal to 0. Now, all right, so when x and y basically have nothing in common, our cosine is 0. So that's basically, yeah, we don't have like words in common, all right? So we get a similarity, a cosine of this theta is 0. So again, cosine of theta is going to be our similarity score. And when our theta is 0, though, our cosine of 0 is equal to 1. That's a perfect match. So when x and y are exactly the same, we can't get anything better as far as a score exists then. All right. Which would imply, again, that these are highly similar, So, okay. Let's move on. Now that we've reminded ourselves of the basics of math, of taking the cosine of the angle between two vectors, let's apply this to our retrieval. We're going to represent both the query Q and the document D as, again, I said, n-dimensional vectors. And where we have document sub T is the weight of term T in the document, and Q sub T is the weight of term T in the query. All right. Now with that, we're ready to do our similarity between the query and the document. So cosine, yeah, I'm just gonna get out a brand new pen. I hope to make it to the end of the term with pen. All right, cosine of query and the document is equal to summation from term 1 to n. So again, where n is our number of words, or it's the size, number of dimensions that we have in our vector space. So again, I mean, suppose you could have something other than words and documents. So instead of your columns being words, you know, you could, there's all this wonderful work that's been done on, having a moment where I can't remember the terminology, where latent semantic indexing. Latent semantic indexing actually transforms the matrix into another space. And in that dimensions, the dimensions there are the main factors of the other matrix. And so it's possible that you could be doing vector space retrieval on things other than words. It could be on concepts and things like that that have been computed from the query document, the Word document matrix. Anyways, in our case, it's definitely the words, all right? And so you take d sub t, multiply by q sub t, all over, then the square root, where we do a summation, again, from over all the terms, and the document. So these are all the elements of the document squared, multiplied. So we're going to multiply in here, just so you know. Then by the summation, t is equal to 1 to n of q sub t squared. All right. So again, this is just the same math that we wrote, but showing you in terms of how you're going to actually compute this. You're going to be able to go through your vectors. You know, vectors are like arrays, and you're going to go down, you're going to do this multiplication, and then you're going to have down here the same thing where you're going to be basically figuring out their lengths and multiplying them. All right. So that's cosine similarity. Great. Now what we need to do is we need to figure out how should we actually be coming up with, so d sub t is the weight of term t in the document, and q sub t is the weight of the term in the query. What should we use as our weights? This is what we're going to, once we have those weights, we can crank this computation, but the magic is going to be in the weights and coming up with the right weightings. So let's do it. All right. So I'll put this question on the board. How should we determine the weights of terms in a document? And likewise, query, just to be clear. All right. Okay. So you could do it as follows. You could be binary, weights with 0 for non-presence. So that word does not exist in the document. And 1 for presence. And I'm just going to let you know this does not work well. Okay, that's the simplest scheme that I can envision for vector space. Oh, does the word appear? Does the word not appear? It probably works better than doing some Boolean retrievals, but we can do a huge amount better. Oh, weighting scheme. What could we come up with? Oh, yes, TF, IDF. All right, so this works well. So for an individual word in a document, we're going to do something where we take something with regard to how frequently it occurs in the document, its term frequency. We're going to be multiplying it by its inverse document frequency, basically how rare it is in the collection. Rare words that occur frequently in a document should get a big weight in my document vector. All right. And if you are a common word, you should not get a very big weight for, and likewise, the more, in general, the more often you appear, the larger your weight should be. All right. So that works well. So let's go ahead and dig into this then. What would be a good weighting scheme? We could put as a weight for term T sub k in document D sub I is going to be equal to the following. So this is the cell in the in our documents by word matrix. What is that weight that we're going to give there? So weight I sub k, we're going to set it equal to the log of f sub I k plus 1. And we're going to multiply that by the log of n divided by n sub k. And we're going to then go over the square root where we have a summation from k is equal to 1 to n of the log of f sub I sub k plus 1 multiplied by the log of n divided by n sub k. All right. Whew. That's all just for one weight. What does this all mean? Well, f sub I sub k is the occurrence frequency of dk and di. So this is the term frequency. How many times does this term occur in the document? Okay. N is the number of documents in the collection. N sub k is the number of documents that contain T sub k, so the kth term, and n, plain old n, which is a good question. Oh, this n, like where's the n in the equation? I lost it. Where n like is number of unique, so our vocabulary size, unique words in collection. All right. So let's break down what this weighting is. What do we see here? This is the weighting that is the representation of our term frequency. And note, we are taking this term frequency but we're taking this logarithm of it. You're going to see this idea show up elsewhere. But basically, one of the things that we're doing here is saying, you know, I want a method for the importance of how often this word occurs in this document that grows fairly quickly at small values. So 1 versus 2 words, that's still a pretty good leap between 2 words and 1 word. And then from 3, it's not quite as big of a leap, but 4, it's not quite a leap. But it keeps, in other words, it keeps growing no matter what. The more words I have, the bigger this is, but the value of later words is not as much as the values of the first words I had. And this is reflective of what we understand with the nature of language and documents. Sure. Oh, well, you contain those words. That's good. Oh, you contain a lot of those words. That's great. Oh, you contain a gigantic number of them? Well, if we're thinking about, is it about that idea, that word, you kind of saturates at some point. And so we don't need to, you know, oh, 2,000 versus 1,000 occurrences. Sure, 2,000 is more than 1,000, but I don't really care. At that point, yeah, you've got your point across. This document has got that word in it, all right? And it's probably about that, all right? This here is formulation for IDF. All right. Then down here, this whole bottom portion, this is the length normalization. All right, that we need to take into, need to deal with. Again, our individual elements are in here. And so then this is got the length of our vector. And so this is what we're computing here. All right. This helps us. And in the cosine similarity world, you know, you could be like, well, why don't I just have this why don't I just use these weights and do the dot product of those weights? Why do I always have to be dealing with this notion of the angle and I'm going to divide by the lengths? It comes down to, this involves dealing with short versus long documents. You know, the nature of it is that a long document is likely to have many more words in common with a query. But should it just be given? Should it really have that advantage just because it's longer? Maybe, maybe not. Short document has fewer words. It's sort of trying to equate and put the short words and the long words sort of more on their equal footing. All right, there's one thing important to note though about this, which is when f of I k is 0, so when we do not have the occurrence of this word in the document, then we set log of f sub I sub k plus 1 to 0. Okay. So this whole thing, if this is 0, we set this whole thing to 0, which then of course zeroes out the entire thing, which, look, again, remember back to, we're eventually going to compute this with inverted indexes. Basically what we're saying is that we're not going to find, you know, so if a document doesn't contain a word, its weight is 0. And it's going to be reflected in our inverted indexes. We're not going to see any count of that word in the inverted index. We're just going to be able to naturally skip over this, and it's going to be going into summations as 0, and it all works out really nicely then. All right. So in fact, we set it to 0 mathematically, but the truth is we just never compute it. All right. All right, so with those weights, you've got those for the document. And you can go ahead. I should actually double check. So this is for the document. I should double check to see exactly what we say for the weighting of the query. Could be exactly the same. I should double check. Anyways, this is the key idea though, is that we end up with the weights that we have in those document vectors being TF IDF weights. And here's an example weighting scheme. And you can see how it evolved over time to not just be simply the term frequency and the inverse document frequency. People ended up with these notions of term frequency and inverse document frequency. And there's a whole bunch of other weighting formulations that people have come up with for vector space retrieval. There's probably some that are even better than this, but this conveys the basic idea. All right.